Hello everyone, I am Anmol Kapoor and I have been allotted lecture number 11 as video assignment. Lecture 11 covers basics of Poisson random variable and we are going to discuss a brief theory about the topic and do the question after this. So what is Poisson random variable? Poisson random variable is basically an approximation for calculating probability by taking probability mass function to be equal to e की power minus lambda into lambda की power I upon I factorial. Note that this Poisson random variable equation is satisfied if lambda is a finite quantity. Also, the expected value or the variance of a probability distribution would be equal to parameter lambda of this Poisson random variable. And if we want the Poisson random variable to be in justification with Bernoulli's, then lambda has to be equal to n into p. The proof can be seen in Ross' book. And therefore, if n is tending towards infinity, then p should tend towards 0 for having lambda to be a finite value. So coming to the problem statement, it is given to us that 1 nanogram of plutonium, which is a radioactive material, it has 6.9 radioactive decays in 3 seconds and it follows Poisson distribution. So first we are going to justify that why the Poisson distribution thing is correct. We know that 1 gram is having 6 into 10 to the power 23 atoms. Therefore, 1 nanogram will have order of 10 to the power 14 atoms, which is very large. So lambda comes out to be a constant because n is very large and p is therefore very small. So lambda can be taken as a finite value and therefore we can use it in Poisson random variable equation. We are asked to calculate the probability that in 1 second period there is exactly x radioactive decays. Now use it in this equation, and for using it in this equation we are going to first put small x in place of I, and after that we're going to need this lambda. Lambda, as I said on this slide, can be taken as the expected value or the variance. Here it is given that 6.9 radioactive decays happens in 3 seconds. So expectedly 2.3 radioactive decays happen in 1 second. Therefore lambda can be taken as 2.3 decays. So putting in the formula, I got e की power minus 2.3 into 2.3 की power x upon x factorial as our final formula. You are also asked to plot it on graph. So putting various values of x, especially 0, 1, 2, 3, 4, 5, we got this as our graph. Here it can be seen that x tends to infinity makes the probability more closer towards 0. We are also asked the probability of having radioactive decay greater than or equal to 6. We know that probability of x is equal to 1 minus probability of x complement. So we are going to say that required probability is equal to 1 minus of probability of having decay less than 6, which is 1 minus p0 plus p1 plus p2 plus p3 plus p4 plus p5. And here putting the values of different probabilities from this graph, we got 0.035 as our required probability, which is very low. It is approximately equal to 0. So, and it is fully justified with the graph that as value is more than 6, the probability tends closer to 0. Also, we are asked to calculate probability if we would have double the period of observation. That means if instead of taking 1 second as our observation, we would have taken 2 seconds. So in that case, the expected value would not have been 2.3 second radioactive decays. It would have been instead 2.3 into 2 decays, that is equal to 4.6 decays, because we are observing for 2 seconds. Therefore, probability would have been e की power minus 4.6 into 4 की power 0.6 की power x upon x factorial by taking lambda is equal to 4.6 decays. So it is equal to e की power minus 2.3 into 2 की power x into probability for 1 second observation. Therefore, we got that the ratio of both the probabilities, that is for 2 seconds and for 1 second period, is having 2 की power x as its term. So it is dependent on the value of radioactive decay. And I think there is nothing after that. So question is complete. Thank you.